We face a challenge without precedent. The goal of reducing emissions and preventing global temperatures from reaching unsustainable levels is already a priority for the UN and the great powers. 40% of the energy we consume is related to the buildings where we work, live, or carry out our daily activities. This causes that a large amount of heat is condensed in cities and urban centers, what we call urban heat island. Creating materials that help to solve this problem is one of the main challenges of science, and for several years, progress has been made. The recent discovery of daytime radiative cooling materials was a first step in creating materials capable of cooling themselves down during the day. Daytime radiative cooling materials bring two key properties together. On the one hand, they prevent solar radiation from entering the material by maximizing the reflectance index. On the other hand, they focus their thermal radiation to a small frequency region close to 10 microns, where the atmosphere is transparent, the so-called atmospheric window. In this way, the heat emitted can pass through the atmosphere without being reflected back, avoiding the greenhouse effect. Now, Miracle Project, led by CFM under the H2020 program, opens a new horizon by bringing this concept to more common and accessible materials, making progress with high impact in the area. The project envisions a new science and technology that turns low-tech concrete and cement-based materials into high-tech functional photonic metamaterials. The result will be a revolutionary photonic metaconcrete, PMC, whose response to light will be engineered for exhibiting a great capacity to cool down. This ability is obtained by new designs, where an ordered arrangement of the steel microfibers can work in combination with the hierarchical porous structure of concrete as a PMC. It is a cheap, scalable, and high-impact solution, technologically unfeasible until the advent of photonic metamaterials. It is now possible to carry out thanks to advanced optimization methods based on deep learning technologies and an inverse phase fabrication methodology. The project will not be limited to research and investigation, but will prove the feasibility of this idea by developing for the first time a radiative cooling device based on a PMC. The fabrication of a prototype whose radiative cooling performance will be validated on the roof of a real building, where its potential environmental impact and application will be evaluated and explored. Communication, solar cell technology, and beyond. If the project confirms expectations, it will be a breakthrough, not only for science, but for the whole of society. The global challenge of preventing the temperature from rising by 0.5 degree before 2030 would no longer be a chimera.